All right. Yeah, so I'd just like to thank the organizers for having me here. It's been a really nice conference and a really nice place. So I just wanted to tell you a little bit about some of the work I've been doing on the dynamics of impurities in quantum gases. And I should mention, so I'm from Monash, and I'm part of this Center of Excellence that's recently been funded at Monash. Okay, so I thought I would just start with a motivation about why are impurities interesting. So I'd like to think of it as the sort of simplest many-body system that one can consider. So where you just take an impurity atom of some kind, or a purity particle, stick it in some kind of quantum mechanical medium, look at how it behaves in that medium, and hopefully gain some insight into more complicated quantum systems. For instance, if you started adding many impurities, or building up a whole quantum system of your impurities. So hopefully by understanding how a single impurity behaves in your quantum system, you can build a picture of how the whole system behaves. And in particular, okay, there are concepts related to how, say, a mobile impurity, so an impurity with a finite mass moving through your medium, behaves. The idea of dressing your impurity with excitations of the medium, so I'll comment on that a bit on the next slide. There's even interesting physics if the impurity is fixed, so it has no mass, effectively infinite mass, and you can have the so-called orthogonality catastrophe for a single impurity, where the overlap between say the Fermi system with no impurity compared to the Fermi system with an impurity that interacts with the fermions, the overlap between those two states can be zero, even for a single impurity. So there's some interesting physics surrounding that. And what's nice about now is that you have the possibility of doing very controlled experiments in the cold atom arena. In particular, you can. What I'm going to talk about today is looking at the dynamics of the impurity. So really, so in a sense, it's the opposite of what Jörg was talking about, where instead of starting with a strongly interacting many-body system and going to a non-interacting case, I'm interested in starting from the non-interacting system and seeing how the many-body system develops. Okay, and moreover, you have the possibility of having different types of media, different types of statistics, whether bosonic or fermionic gases that you can place your impurity in. So as I mentioned, what I'm going to focus on in this talk is the idea of the mobile impurity, so with a finite mass, and the possibility of doing looking at it in the context of cold atoms. So so just to flesh out, there's this nice picture that I stole from a classic textbook of Matuk. The idea of when you have an impurity moving through a medium, you can essentially dress it with this cloud of excitations in much the same way that if you had a horse moving through, say, a desert, it would dress itself with a cloud of sand or something like that. So you have this so-called the concept of a quasi-particle, or in this case, a quasi-horse. Okay, so what a common term that's been used in the cold atom system is to call this also a polaron, which is really borrowed from the situation where in solids, where you have an electron moving through a lattice and how it dresses itself with lattice excitations or phonons. Okay, so this is where the term polaron comes from, how it polarizes the lattice, but it's been used to describe, in general, the dressed impurities that you have in quantum gases. Okay, and as I mentioned, that you can have, despite just having a single impurity, it can actually fundamentally change its character in a medium, and in particular, what I find quite interesting in the case of mobile impurity in a Fermi medium is that it can even effectively change its statistics. So, for instance, I think I stole this picture from one of Martin Svilline's papers. But so, for instance, if you increase the attraction between impurity and its surroundings, eventually it can undergo a transition to essentially a dimer, so a bosonic dimer. So it behaves like a bosonic impurity rather than, say, if this was originally a fermionic impurity. So there's a sharp transition from fermionic to bosonic impurities. So you can even have transitions in this impurity system. So, okay, so to the outline of my talk, so I will be telling you a little about a recent experiment that I've been in, where I've provided the theory for this experiment of Rudy Grimm's group, where they looked at the dynamics of impurities in a Fermi gas. And if I have, and so this was done also in collaboration with Jesper, and also there was some nice theory done also by Eugene Demler's group at Harvard. So, if I have time, I'll also give you maybe a snapshot of what the situation looks like in where you have a so-called, well, what's called a Bose polaron, which is where you have an impurity in a Bose gas. But I suspect